Welcome to the fourth lecture of the course Marine Propulsion. Today we will start propeller theory. So, when talking about propeller theories, these theories basically they try to explain propeller action. So, the propeller action of the propeller can be explained using different theoretical concepts. So, under propeller theory we will cover these different theories which try to explain the thrust generation by the propeller by absorbing the input power and also the concept of propeller efficiency. So, in this first class on propeller theory, we will be covering propeller axial momentum theory, which is the basic simple theory for marine propellers, which can be used to explain very simply the action of a propeller using some basic fluid mechanics principles. So, we will cover the axial momentum theory and the concept of ideal efficiency. So, for axial momentum theory, there are some basic assumptions that we make, and it is very important to understand these assumptions based on which the theory is established. So, the first assumption is that the propeller is regarded as an actuator disc. So, in this particular theory, we do not have the propeller as such. So, instead of the propeller, what we have is basically an actuator disc which imparts a sudden pressure jump and it increases the pressure of the fluid, and in that way it generates thrust. So, here we are not concerned with the entire mechanism of action of the disc. So, we are assuming that the propeller is a disc and it imparts a pressure increase to the flow. Next assumption is the propeller works in ideal flow. So, ideal flow means it is the fluid is considered frictionless and there are no energy losses in the system which can come due to friction. So, they are ignored here. And the third assumption here for the axial momentum theory is that the propeller produces thrust by inducing axial velocity over the entire disc uniformly. Here by that what we mean is that the propeller is producing an acceleration to the inflow. We will explain all these things with the derivations, but without any rotation to the slipstream. So, the propeller being a disc, it is only giving a pressure increase to the flow, by that it is generating a thrust, but it is not providing any rotation to the flow. Okay. So, this is, as I have explained, this is a very simplistic theory, this is a very basic theory which explains the propeller action using some very basic fluid mechanics principles. So, the axial velocity that is induced because of that pressure jump is uniform over the entire disc, okay, and there is no rotation. So, next we will move on to the derivation of this axial momentum theory. Okay. Let us take a flow domain where we have the propeller disc or the actuator disc as we say. So, here we have the actuator disc which is basically giving the thrust here. So, we have taken the domain so that it extends far ahead of the disc and to a zone which is far behind. Now, what are the pressure and velocity components in these regions? Far ahead, let us say it is pressure is P0, okay, and a velocity we put at the inlet which is in this direction which is V, okay. Now, we have to remember that the propeller ideally should move ahead in the fluid at a velocity v. Instead of that, we are resolving the hydrodynamics in such a way that we are giving a flow v at the inlet and keeping the propeller fixed. Okay, that is how typically these problems are analyzed. And because of the propeller giving a pressure here jump, we will have an induced velocity at the propeller plane and also far behind. Let us say far behind we will have the pressure here again P0 and V plus UA. Okay. Let us say that is the induced velocity far behind the propeller disc, and here at the propeller plane, let us say the velocity is Vp, where Vp is the velocity at the propeller, and the pressure just in front of the propeller is P1, propeller or the disc here, and just behind the disc is P2. Okay. So, basically what the propeller does is it imparts a pressure jump across the disc here, and because of that it generates a thrust. So, if we try to draw the pressure lines, so here we have a pressure P0, it comes down to a value P1 because of the velocity increase, and then at the propeller disc there is a jump, okay, and then again it comes to a value P0. So, if we consider P0, which is let us say atmospheric pressure at the ends, so the pressure comes to P1 here and with a jump P2, and then we have the pressure coming down in the slipstream. So, if we see, there is a slight contraction of the area here. Here if we see, there is a contraction of the area. Why? Because the propeller accelerates the flow. As the propeller will accelerate the flow through the disc, okay, it will impart a momentum, and because of that acceleration there will be some contraction of the flow because of continuity. Okay. So, that contraction will start slightly ahead of the propeller here ahead, and also end at some position behind the propeller. Okay. So, we are taking the two ends far ahead and far behind the propeller in such a way that the velocity is fully developed far behind. Now, V here will be the velocity by which the propeller is moving ahead. So, we can write as the velocity of inflow. Okay. UA is the axial induced velocity, right. Vp is the velocity at propeller disc, okay, and P1 and P2 are the pressures just ahead and just behind the propeller disc. Okay. So, now if Q is the volume flow rate through the propeller disc, okay, how is Q defined then? We can express Q as area of the propeller disc here. Let us say if area is AP, then multiplied by the velocity of fluid at the propeller disc, because in the momentum theory assumption we have that the velocity is uniformly distributed over the propeller disc. Okay. Now, what is the input velocity to the system is V at the inlet, and at the outlet we have V plus UA. So, the difference in momentum of the system should be of fluid, it should be equivalent to the thrust generated by the disc. So, thrust generated T should be rho Q V plus UA minus V, where V was the velocity at the inlet and V plus UA is the velocity at the outlet. So, thrust is given by rho Q UA, right. Now, what is Q? AP times Vp. So, we can write equal to rho AP Vp UA. Okay. we name it equation 1. Okay. Now, let us take two sections of the fluid, one just ahead of the propeller disc and one just behind the propeller disc. Okay. Now, if we apply Bernoulli's equation, between, let us say, section 0 at the inlet and section 1 here, okay, what do we get? P0 plus rho v square by 2 equal to P1 plus rho Vp square by 2. Here the assumption is we are taking the plane section here just ahead of the propeller disc. So, it is the velocity here is equal to the velocity that is on the propeller disc. Okay. Now, if we write again the equation between the section 2 and the section which is far astern, let us say 3, what do we get? The pressure here at 2 is P2. So, P2 plus rho Vp square by 2 equal to, here the pressure is P0 at 3. So, this second equation we are writing behind the propeller disc, P0 plus rho V plus UA whole square by 2, right. So, we can write this equation by exchanging the terms on the left hand side and right hand side in this way, P1 plus rho Vp square by 2 equal to P0 plus rho V square by 2, right. So, if we name this 2 and name this 3, right. If we see here on the left hand side we have P1 plus this term rho V square by 2, we have P2 here, okay, and on the right hand side we have P0 and the velocity terms square, okay, with rho. So, if we go to the next page, now if we subtract 2 from 3, so if we write 3 minus 2, we get P2 minus P1, okay, this rho Vp square by 2 term will be cancelled, equal to, again P0 will be cancelled, rho by 2 if we take common, V plus UA whole square minus V square. Okay. Now, what is P2 minus P1? P2 was the pressure just behind the propeller disc and P1 was the pressure just ahead, and because the disc is providing a pressure jump, we can write it as delta P, which is the pressure jump created by the disc. And we have to remember that in axial momentum theory we are assuming that this pressure jump as well as the velocity is uniformly distributed over the disc. So, del P is rho by 2, this will be 2 V UA plus UA square, right. Now, again if we write del P equal to, so this pressure jump del P can be written as rho with UA common V plus UA by 2, because this half goes inside the bracket. Okay. Now, let us write it as 4, right. Now, this pressure jump is related to the thrust produced by the momentum disc. How? The thrust produced will be this pressure jump into the area of the propeller disc, right. So, how is the thrust related to the velocity UA? We have already derived it in the last page. Here thrust is rho area of the propeller disc terms Vp into UA, right, equation 1. So, if we write rho AP Vp UA, right. So, if we compare equation 1, this is nothing but equation 1, if we compare that with 4, what do we get? Rho AP Vp UA is equal to rho UA V plus UA by 2, right, into AP, because thrust is equal to del P into AP, area of the disc. So, rho AP will cancel out on both sides and UA will also cancel out. So, we have Vp equal to V plus UA by 2. This is a very important result coming from axial momentum theory. Now, the implication of this result is that the velocity at the propeller disc is the velocity V plus half of the velocity that is induced far behind the disc. That means, at the propeller disc we have the induced velocity component is half of the induced velocity which is far behind the propeller plane. So, this can be proved easily using momentum theory given the assumptions that we have made. Okay. Now, next we will try to find the efficiency of the momentum disk. Okay. For that, we have to calculate the work done by the momentum disk is given by the thrust that it generates multiplied by the velocity against which it generates the thrust. So, here we will not take Vp or any other velocity, it has to be the velocity at which the momentum disk is moving ahead or the fluid is coming here, in this case from the inlet velocity. Okay. So, thrust times the velocity. Now, what is the energy supplied? Energy supplied is basically the difference of the kinetic energy at the outlet minus the inlet. Okay. So, that means rho by 2 into the Q, where we have the mass flow rate Q, into V plus UA whole square. The kinetic energy is basically half mv square. So, instead of the mass we have the density times the flow rate here per unit time, because we are calculating the energy supplied per unit time, V plus UA whole square at the output minus the input energy V plus V square here. So, the ideal efficiency eta I is given by the work done by the energy supplied. So, basically it is the output that we get, which is again the thrust times the velocity, right, divided by the input. Okay. Now, how is thrust defined with respect to the mass flow rate? It will be rho q UA times V here, and in the denominator we have rho q by 2. The expression within the bracket will be 2 V UA plus UA square, right. Now, rho q terms will cancel out each other, right. So, we have 2 V UA by 2 V UA plus UA square. Okay. Again, we would want to make this expression non-dimensional. Okay. So, it is already non-dimensional, but we will try to make both the numerator and denominator non-dimensional so that we can express the velocities as non-dimensional ratios, each of them. So, we divide the numerator and denominator by v times ua. So, what we have here will be 2 by 2 plus ua by v. Okay. This can also be written as divided by 2, it will be 1 by 1 plus ua by 2v. Okay. Eta I. Now, why do we call it ideal efficiency? Because in momentum theory, we are neglecting friction losses and other losses due to rotation and all. So, because of neglecting of these losses, we call it ideal efficiency, because this is the maximum efficiency which the system can achieve if we disregard all these losses. Now, if we see this term here, we only have a ratio of the velocities here in this efficiency term, and basically ua by 2 is what? It is the induced velocity at the propeller plane, because the velocity at the propeller plane Vp was V plus ua by 2, where ua by 2 was the component coming from the induced velocity part, okay, due to the action of the momentum disk. So, that divided by the input velocity, if we write it as a, so let us say it is a non-dimensional fraction. So, then we can write eta I as 1 by 1 plus a, okay, where a is basically the induced velocity at the propeller disk, non-dimensionalized using the velocity of moving forward or the inflow velocity. Okay. So, this will be the ideal efficiency from the axial momentum theory. Okay. So, this will be all for today. So, we will continue with the thrust loading and other calculations regarding the momentum theory. Thank you.